We will now proceed with the process analysis when there are different flow units involved. The concept of the bottleneck becomes apparent when aligning supply with demand within a system. It can emerge due to constraints on either capacity or demand. In the left graph, the bottleneck is defined by the process capacity, since it is smaller than the input, indicating a capacity constraint scenario. Conversely, the right graph portrays a situation where demand is smaller than the capacity, signifying a demand constraint scenario. In essence, the flow rate of the system is determined by the minimum value between the demand and capacity. This implies that the flow rate is retreated by the smaller factor, be it the customer demand or the system's capacity. By comprehending this interplay, organizations can effectively manage their operations and optimize resource utilization to meet customer demands. We will now examine this example. Suppose we have three resources with the following process capacities: 1/5 for resource 1, 1/6 for resource 2, and 3/16 for resource 3. Given a demand of 8 units per hour, the equation is: what is the flow rate? To calculate the flow rate, we first identify the process capacity. Among the three processes, resource 2 sets the limit with a flow rate of 1/6 unit per minute. Thus, the process capacity is 1/6 times 60 equals 10 units per hour. Next, we can calculate the flow rate using the formula flow rate equals minimum of demand process capacity. Substituting the values, we find flow rate equals min of 8 and 10 equals 8. Therefore, the flow rate is 8 units per hour, which precisely matches the demand in this scenario. Utility and implied utility are two concepts that help analyze the relationship between supply and demand in a system. Utility is defined as the ratio of the actual average flow rate to the capacity of a resource. For example, if the actual flow rate is 8 units and the capacity is 10 units, the utility will be 8/10. On the other hand, implied utility is the ratio of demand on a task to its capacity. In this case, if the demand for a task is 8 units and its capacity is 10 units, the implied utility will be 8/10. When considering which concept is more useful, implied utility proves to be particularly valuable. It captures the mismatch between supply and demand, allowing us to identify situations where demand exceeds the capacity of a task. By highlighting this mismatch, implied utility helps to pinpoint potential bottlenecks and areas where adjustments or improvements may be necessary in order to better align supply with demand. To analyze the process with different types of flow unit. We will examine a case study in the context of job applications. Specifically, we have three types of job applications: consulting, staff, and internship. Each application type follows a distinct path through the process, and not all tasks are visited by every application type. The consulting application goes through the tasks of contacting faculty, contacting prior employers, and finally, receiving a decision letter. The staff application involves contacting prior employers before proceeding to the decision letter. In contrast, the internship application directly goes to the decision letter task. It is worth noting that there are inventory buffers located in front of each resource or task, although they are not depicted in the diagram. To facilitate the analysis of the process, it is essential to define a common flow unit that satisfies two criteria. Firstly, the capacity of each task should be expressed in terms of the flow unit per unit of time. Secondly, the demand for the process should also be expressed in terms of the flow unit. In this case, an intuitive and fitting flow unit for the process is an application. By considering an application as the flow unit, the capacity of each task can be defined as applications per unit time, and demand for the process can be appropriately expressed as applications per unit time. However, as there are three different types of applications, it poses a challenge in evaluating the process capacity and demand accurately. To address the challenges posed by different types of applications, we resolve the issue by defining the flow unit as 1 minute of work based on the provided demand data. This ensures consistency, allowing us to express both demands and capacities in terms of minutes of work. Taking the example of the contact employers task, we recall that the demand for this task is 14 applications per hour. It is important to note that each application requires 15 minutes of work. By multiplying the number of applications, 14, by the work time per application, 15 minutes, we find that the demand for this task per hour amounts to 210 minutes of work. This calculation allows us to accurately quantify the hourly demand for the task using the selected flow unit. We now determine the bottleneck of the entire system. It is important to note that defining the flow unit as 1 minute of work or one application yields the same implied utilizations. The implied utilization does not depend on how the flow unit is defined, as long as all demands and capacities are defined consistently. Next, let's compute the total demand for each resource. For the contact faculty task, with the 3 applications per hour, and each application requiring 20 minutes of work, the total demand is 3 multiplied by 20, resulting in 60 minutes of work. Similarly, The contact employer's task has a demand of 14 applications, and each application takes 15 minutes, totaling 210 minutes of work. The benchmark grade task requires 3 applications at 8 minutes each, amounting to 24 minutes. Lastly, the decision letter task involves 18 applications at 2 minutes each, totaling 36 minutes. Moving to the capacity side, each person has 60 minutes per hour available for work. Thus, the contact faculty stage with 2 persons has a total capacity of 120 minutes of work. Likewise, the contact employees stage, staffed with 3 employees, has a capacity of 180 minutes of work. The benchmark grade task, handled by 2 employees, has a capacity of 120 minutes of work, while the decision letter task, assigned to 1 employee, has a capacity of 60 minutes of work. To identify the bottleneck in a system with multiple flow units, we calculate the implied utilization for each resource. For the contact faculty task with a demand of 60 minutes and a capacity of 120 minutes, the implied utilization is 60 divided by 120, resulting in 50%. For the contact employee task, the total demand is 210 minutes, and the capacity is 180 minutes, leading to an implied utilization of 210 divided by 180, which equals 117%. The benchmark grade task has an implied utilization of 32 divided by 120, or 27%, and the decision letter task has an implied utilization of 36 divided by 60, or 60%. The bottleneck is determined by the task with the highest implied utilization. If a bottleneck has an implied utilization greater than 1, it is referred to as a binding bottleneck because the capacity has been fully utilized. In summary, to conduct basic process analysis with multiple types of flow unit, we can follow these steps. First, compute the production capacity of each resource by determining the number of minutes it can produce. Next, create a process flow diagram that illustrates the movement of flow unit throughout the process. Then, construct a table that specifies the workloads consumed by each flow unit at each resource. Sum up the workload for each resource across all flow units. To determine the implied utilization of each resource, divide the workload from step 3 by the production capacity from step 1. Finally, identify the resource with the highest implied utilization, as it represents the bottleneck in the process.